Welcome students. So today we will start a new topic called cognitive radio. Okay. So this is a very you know relatively newer topic within wireless communication, but its impact is very widespread. So we will go through cognitive radio concepts in today's lecture. So this is basically a topic which you won't find in your textbook. As I said, this is a relatively newer topic. So most of the stuff that I will discuss today in cognitive radio, um, you will find them in the lecture notes that I'm going through right now. And also, if you want, you can look for a lot of references in the internet. You can search them on your own. If you type the term cognitive radio in any search engine, you will find loads of references. I will also try to give you some references to read, but let us first go through the, the presentation that I have, and let me try to explain in a high level the concept of cognitive radio, and then I will redirect you to some references. Okay, so the term cognition, if you just look into the plain English meaning of the term, so basically this is something related to the thought process. So let us read out the actual definition. So cognition is a noun which means the mental action. So the term mental here is important. The mental action or process of acquiring knowledge, okay, and understanding through thought, okay, experience, and the senses. So you can see this term cognition is associated with like mental action of acquiring knowledge and understanding through thought, experience, and the senses. So this is something which, as human beings, we all have. Okay, so you and me, we all have our brains, and we actually have the power of cognition. Okay, so in terms of physical devices and electronic devices or IoT devices, uh, the the concept of cognition is a very big deal. Okay, so for human beings like you and me, even for some animals, this concept of cognition is quite natural. But for an electronic device, um, or a computer, or anything that is built up of electronic chips, the concept of cognition, or the act of putting cognition into those devices is a big deal, and it's a technological advancement in itself. So these days we all talk about AI, artificial intelligence, and machine learning, etc. So all these fields are now getting very popular, and we are applying them, uh, and I'm trying to put some form of um, artificial intelligence into the modern devices, the IoT devices. So cognitive radio, this field of research was relatively you know um, older. It was like 20 years back it all started. Okay, but even before that, I'm not an expert in researcher in cognitive radio, but that's what my guess is. So this is a relatively older term, but This probably was the first instance of putting intelligence into a communication device. Okay, so cognitive radio is a pioneering field in itself, because today we all talk about AI, machine learning, etc., and how to put intelligence into these communication devices or IoT devices. So it's all started with cognitive radio. So we will go further and see how this evolution of cognitive radios happened. So traditionally we had these traditional radios, okay, and then the transition came to software defined radios, okay, and this probably marked um, the beginning of cognitive radios. And then finally you have cognitive networks. So if you put multiple cognitive radios into a network, then you can have a cognitive network. So so this was the evolution path, okay. And if you look into the different components of that evolution, so as I said, the software defined radio, or SDR, is actually a very important milestone towards the development of cognitive radio. So software defined radio, what is the difference between software defined radio and cognitive radio? So in software defined radio, you have a collection of hardware and software technologies that enable reconfigurable system architectures, okay, for wireless networks and user terminals, okay. So so this means that you have a software, okay. So you have a software, okay, that runs, let's say, a radio, okay. So by radio it means any device that has a transmitter and a receiver, and it's transmitting and receiving at a certain frequency, okay. So your mobile phone has a radio, okay. So don't get confused with the term radio, which in olden days used to mean a device which you can listen to, and you can listen different audio programs. So that was the traditional term of the radio. But in modern terminology, the term radio means any device that is capable of transmitting and receiving at a certain frequency. So your mobile phone has a radio, your laptop has a radio, and so any device which has a communication capability, wireless communication capability, will have a radio. So now, given that you have a radio, now you have a software that controls this this radio, okay. So basically the radio has some hardware components, and then there are some software which you you can code, okay. So some expert software engineer will write a code to to be able to control and manage this radio, and the same engineer or another person who has enough knowledge of this software can make some changes. Let's say a code is written, and inside that code you change some parameters, okay, or some variables, and then the functioning of this radio can completely change. So that's what is meant by reconfiguration. So you are basically making some small changes in this software to reconfigure the functionalities of this radio, okay. So that's what is software defined radio, okay. Now if you look into the definition of cognitive radio, so this is a radio that is aware of and can sense its environment, okay. So this is important, and can make decisions about its operating behavior based on that information and predefined objectives. So So what's the difference that you found? So this one uh, has a software, and you can change that software and reconfigure the radio. Okay, so the radio is actually behaving as a dumb device. Okay, and you as a human expert who is controlling this software, who has written this software, you can change this software, and then the radio behavior changes. But here in this case, this radio has some form of cognition, because it is aware of and can sense its environment. Okay, so it means that the radio has some intelligence built on top of it. Okay, um, that will sense the environment, and by sensing the environment means that it can collect data from its environment. Okay, and based on the changes in that collected data, it can provide feedback to the software that is controlling it. Okay, so that is what happens in case of a cognitive radio. It is aware, and it can sense its environment, and then can make decisions about its operating behavior. So these decisions are fed back to the software which is controlling the radio, and then there will be some changes in the software, let's say in an automated fashion. Okay, and then the radio can change its operating behavior. So that is cognitive radio for you. Okay, so there is a difference between software defined radio and cognitive radio. So let's now look into a more detailed definition of a cognitive radio. So a cognitive radio is a transceiver. Okay, so transceiver means transmitter plus receiver. Okay, so this is the combination of these two terms. So this term transceiver, this is a technical term which we use a lot, which means that a transmitter and receiver together. And you saw we were discussing in the previous slide that a radio is any device that will have a transmitter and a receiver, right? So the definition of cognitive radio says that a transceiver that is aware, adaptive, and capable of learning from experience. So what should it be aware of? It should be aware of the RF environment. Okay, so what communication waveform features are there, what are the channel characteristics. So if you recall, the wireless channel is fading in nature. Okay, so it has that multipath components, and because of that the channel characteristics might change. So the radio should be aware of the changing RF environment. Okay, it should be aware of its own capabilities, so how much power it can consume, what is the DSP clock rate, what are the device operational status, etc. It should be aware of the policies it needs to follow. Okay, so the policies, by policies you mean like whether it can operate on a certain set of frequencies or not, or all those things. So it should be aware of policies it needs to follow. It should be aware of the local and global objectives. So it should be aware that um, whether it needs to um, maximize the data rate. Okay, or let's say minimize the power consumption, etc. So these are the objectives. Okay, so it can be local objectives or global objectives. So maximize data rate, minimize power consumption, this can be both global and local objectives. Okay, and then there could be other objectives as well. For example, maximize the usage of the link bandwidth, okay, all these things. So it should be aware of those objectives. It should be aware of the network conditions, okay. So whether the network is heavily loaded or the network is lightly loaded, etc. It should be aware of other users' priorities and authorizations, okay. So so many things it should be aware of. So this is truly cognitive in nature. And then it should be also adaptive, okay. Not only it should be aware of all these characteristics, okay, it should be also, you know, adaptive. It should be also adaptive. Being aware of those different characteristics is not enough. It should be adaptive to these things. So after getting that awareness, it should behave in a way that it should change its, you know, its operating characteristics, so that you can have maximum benefit. So that's what is meant by it should be adaptive. So adaptive of the transmit power control, adaptive of the dynamic waveform selection, adaptive of dynamic spectrum access, adaptive of block edge mask, routing, negotiation of waveforms and protocols, etc. So, and also the third feature is that it should be capable of learning from experience, okay. So this is also important. So it should be whatever data it gathers, okay, it should be able to make some inference out of those historical data. So this is what is meant by learning from experience, and that's where machine learning algorithms come into play, okay. So this is the formal definition of a cognitive radio or a cognitive transceiver, okay. So I'll show you a video to give you some concepts, I mean the high level concepts of cognitive radio, but in a funny manner. So I will stop here and I will play the video, and I will come back after the video.
One day, Basil takes his dog Pepper for a walk at the marketplace. Basil needs to buy a new collar for Pepper. While Basil is not paying attention, Pepper wanders off. He finds an enchanting collar on the ground. The imperial servant assumes Pepper is one of the princess's many pets and lifts him into the carriage. When Basil sees what's happening, it's already too late. He is not allowed to use the imperial lane because of the strict traffic rules. This is in fact exactly how wireless communication works today. Mobile devices are only allowed to use certain frequencies which are getting crowded. New music and video services on the internet require far more bandwidth than is available for the current networks. With cognitive radio technology, we can use all available frequencies, even those dedicated to TV or satellites. The intelligent devices negotiate in order to use the whole radio spectrum in the most efficient way. This way, we can multiply the current network speeds. Basil arrives at the town gates. But to enter the town, he has to fill in a stack of forms. He has no time for this kind of nonsense. But hey, what's that guy doing there? He's filling out all the forms just by the push of a button. With cognitive radio, you can easily control and verify your identity both online and offline in one simple step. For instance, when you move, you could redirect your mail, subscribe to electricity, gas and water, enroll your children at a school, and even register to vote. all at the same time. Although your device is capable of connecting with any institution, you would still be in charge of the information you choose to share. Basil comes across a billboard advertising an event at the arena. He can't understand the language, but the radio-enabled billboard sends his handset the information he needs, which he then shares with his friends. By the word radio, we mean any kind of wireless communication. At the moment, radios can communicate only with other radios of the same kind. Cognitive radios could understand the language of any radio. This, combined with new simple radios embedded in any object, would allow interaction between any physical objects. This could also provide solutions for communication between people of different languages and cultures. At the arena, Basil sees Pepper in the imperial box with the princess. Basil hears somebody coming. Suddenly, Basil has become a part of the main event. He can't even lift his weapon. Running for his life, Basil pushes the panic button on his device. At a concert, a football game, or any big event with tens of thousands of people, the local network may get overloaded. With current spectrum usage limitations, the provided capacity just isn't enough for all the users. Cognitive radio can use all available frequencies and connectivity methods. It can quickly adapt to the unusual situation and ensure proper operation of the networks. The devices connect not only through the network cells, but also by forming spontaneous networks. This way, messages, phone calls, and even real-time video streams can be transmitted by many more users. One of Basil's friends finds information about the lion. This gives him an idea, and he tells everyone about his plan. A flashlight distracts the lion from the chase. Basil suddenly realizes this may be his opportunity. Success! The undefeated lion is caught! Basil has done the impossible! Basil is escorted to the winner's lounge to wait for the princess. Here she is, Her Imperial Majesty. Oh dear, this won't go well with the princess.
So welcome back after that interesting video. I hope you enjoyed that. So let's now revisit the evolution of this cognitive radio. So you have conventional radios first. So this is basically a combination of traditional RF design and then the traditional baseband design. Okay. So then came the software defined radio or software radio. So this was a combination of conventional radio plus the software architecture, especially reconfigurability and provisions for easy upgrades. Okay, so if there are some new features to be added, you can just make some changes in the code, or you can append some more lines to the original software that was driving the radio, and then you can make easy upgrades. Okay. Then the cognitive radio has all the features of a software radio, so SDR, plus you have intelligence, awareness, learning, and observation. So that's what we have for cognitive radios. So usually in a cognitive radio, you will have a cognitive engine, okay, and then there will be some objective function, okay. So as we were talking about a few slides back, we have objective functions like either maximize the SNR or maximize the data rate, etc. And then to achieve this objective, okay, you need to follow some policies, okay. So the policies are basically the allowed frequency bands for primary and secondary use, okay. So when you say primary or secondary in the context of cognitive radio, it means that the primary users are the one who are using the licensed spectrum, okay. So if you recall your first few lectures in wireless communication, you will see that there is a big issue regarding the licensing of the spectrums, okay. So the government of different countries, they actually regulate the spectrum usage, and then if you want to use a certain portion of the spectrum, then you have to buy a license from the government, okay. So primary users are the one who are who have paid the price and using the licensed spectrum. The secondary users are basically the cognitive radio users, okay. So when you mention about cognitive radio, so as you saw, cognitive radio has some form of intelligence and some form of sense, okay. So basically a cognitive radio uses its intelligent and its sensing capabilities to find out the spaces in the spectrum, okay. So let's say if you have a band of frequencies, okay, let's say like this, and let's say your primary users are using this part, let's say, and then again this part, okay. So let's say these are your primary, okay, users or the licensed users, okay. So now you see that there are some empty slots in the spectrum. So the cognitive radio actually tries to sense these empty slots in a spectrum, and then they try to use these slots, okay. Now whenever they find a free space in the spectrum, they will try to use that. So essentially cognitive radios are the secondary users, okay. So it should know, okay, what are the allowed frequency bands for primary and secondary use. So these are the policies that it needs to know so that it can achieve this objective function, okay. And then there are certain meters, okay. So for example, what are the occupied bands, okay, what's the signal strength, what are the neighbors or what are the interferers that it can have, all these things. So all these informations are input parameters or the meters that the cognitive engine needs to know. And then there are certain knobs, okay, so which you can tighten up or loosen up. So for example, what will be the power, what will be the frequency of operation, what will be the waveform used, etc. So based on these meters and the policies, the cognitive engine tightens these knobs and then tries to achieve these objective functions, okay. So these are the different parts of an entire cognitive radio. Now moving on, what are the desirable features of a cognitive radio system? So the first feature is that it should be wideband, okay. So wideband means it can occupy any spectrum. So as you saw that it's basically operate on the free spectrum slots like this. So you never know which part of the spectrum will be free. Okay, so this is one example where you have these parts are free. There might be a scenario where, let's say, only this part, only this part is free. Okay, so the cognitive radio should be able to operate in any frequency band from here to here. So basically there is a very popular term that the cognitive radio engineers use. It's called DC to daylight. Okay, so DC means zero frequency. Okay, as you might have known. Okay, so if this comes from the Fourier series analysis. Okay, so you have a DC component and then you have the other frequency component. So DC means the zero frequency component, and daylight means in daylight you have all the possible frequencies that you can have. If you consider the 7 colors of the rainbow, okay, the daylight or the sunlight actually can be split into different colors or different frequencies. Okay, so basically a cognitive radio should be as wideband as DC to daylight, so from zero frequency to the maximum possible whatever it is. Okay, so that's what is meant by DC to daylight. Then it should be able to support any waveform. Okay, it should have a flexible architecture, it should be high performance and low power consumption, it should be affordable and accessible, it should be relatively straightforward to use and innovate with, it should be robust, and it should access to suitable frequency spectrum segments for innovation and testing. So these are the different features of a cognitive radio system. So usually a cognitive radio is a combination of hardware and software, as you can appreciate by now after listening to this lecture so far. So you have this cognitive engine, and then you have the policy engine. Okay, and then you have this different layers of the communication protocols, and then you have this policy domain which is communicating with the policy engine. The policy engine is communicating both ways with the cognitive engine, and then the user domain is there. Okay, so this is for writing the software. Okay, for the cognitive radio. So there, as you can see, there are different domains, and they have either bidirectional or unidirectional, relationship with the other domains. Okay, so this is the physical layer or phi layer of the cognitive radio, and any software defined radio can go here. Okay, any software defined radio can go here, and the other parts, or more specifically the cognitive part, can be added on top of this by the combination of this cognitive engine and the policy engine. Okay, so one example of a cognitive radio is GNU radio. Okay, so this is free and open source. You can go to this link and have a look. Okay, so it consists of communication system flow graphs which can be built out of discrete components. Okay, there is one repository per component. The different components that the GNU radio cover are sources and sinks, filters, different math parts like add, subtract, multiply. You have different probes. For example, there will be some graphical user interface windows, power probes, etc. You can have different signal processing elements, and then the main code can be written by Python or C++. Okay, so this is an example of the GNU radio. So this is how the interface looks like. Okay, so you can build the system flow graphs like this, where there are different repositories here. Okay, so this is an example of a wideband FM receiver. Okay, so these are the different components of the FM receiver, and then here is the library of different blocks that you can use. So you can use them, and then if you compile the whole system, then you can have a cognitive radio system. So this is the software part actually. So this would run on radio, which is the hardware part. Okay, so this will run on top of a radio as an embedded program. So another example of the cognitive radio is Iris. So Iris was actually developed at Trinity College Dublin. Okay, so I was before joining UCD, I was actually in Trinity College Dublin as a postdoctoral research fellow. So I was aware of this test bed, this Iris. So this is also a cognitive radio test bed, which was developed by a startup company called Software Radio Systems. So again, you can go to this link and look up for more details. So this is a reconfigurable radio testbed on a general purpose processor platform, and it is designed to facilitate dynamic reconfiguration, and it is platform independent. It has a large inventory of signal processing components. It has sources and sinks, math, signal processing, communication, everything. Okay, so moving on. So this is the schematic diagram of the Iris operation. Okay, so as you can see, there is a radio component, then there is a XML parser, then there is a component manager. So then there is a radio engine, and then there is a control logic, and then you have the Iris API. Okay, so each of these components have different function, and then you have these reusable radio components which you can borrow. So the component manager, okay, can borrow the radio components and then build the radio engine. So the different functions of these blocks are as follows. So the radio component is the basic unit of the Iris implementation, and it comprises an individual stage in the signal processing chain of an Iris reconfigurable radio. The actual level of functional complexity that a radio component may have is at the discretion of the radio component designer. Okay. However, a wide range of components exist. So as you can see from here, and you can build, okay, different systems, different unique systems out of these components. Then the XML parser, any given radio implementation is defined by this XML parser. Okay, so this is used to interpret the radio design specified in the XML configuration file and convert this information into a form that may be processed by the component manager and the radio engine. The component manager, as I said, loads the radio components. Okay, and then The component manager loads the radio component specified in the XML configuration file and unloads a previously loaded radio configuration. So the component manager also compiles an inventory of components which may be located either on the host PC or from a remote location connected via internet, and these comprise the available components that may be used as a part of a radio implementation. The radio engine is the core of the IRIS framework, by the way. So this implements the radio design to create an actual reconfigurable radio using the IRIS framework as the management and controlling entity. Then the control logic manager is basically used for reconfiguring a radio configuration when the radio is in operation. So this radio management feature can access the structure and parameters of all the components and modify them as required. And finally, the API, the IRIS API is used to integrate an IRIS reconfigurable radio application into other applications. Specific functions that manipulate and control the IRIS framework are abstracted from the core of the IRIS system, enabling the sophisticated IRIS features to be accessed using a simple programming interface. So this is the entire operation of the IRIS software radio, cognitive radio system. So this is the website, you can have a look. So this is the CREW project which talks about the IRIS testbed. Okay, so you have some demonstration videos here which you can look. If you go to this website, crew-project.eu, you can find out all these details. Okay, so now moving on with the general concepts. So you have in any cognitive radio you have that hardware part, and there is a trade-off. Okay, so you can build the hardware either on general purpose processors or DSP chips or FPGAs or ASICs. Okay, so if you go from right to left, then you have more efficiency in terms of speed and power. If you go from left to right, you have more flexibility. So there is a design trade-off, you can see. So this direction is good for logic and cognition, and this direction is good for signal processing. So depending on what you actually want to achieve, you can choose either of these blocks. Okay, and then there is always a radio front end. Okay, and then there is a radio and signal processing software. So the front end deals with frequency, filtering and power. Software handles the waveforms and the protocols. So these are the examples of some SDR RF systems. So you can have Softronics, you can have Motorola, then you can have Lartec, you can have USRP. So there are many options that you can avail. So now let us look into the applications of cognitive radio. So the first and most important application is dynamic spectrum access. As I was saying few slides back, that cognitive radio system can access the free spaces in the spectrum. So that's what dynamic spectrum access is all about. We will talk about it in details in a few minutes, but let us see the other applications of cognitive radio. So you can have cooperative medium access and cooperative communication. You can have opportunistic switching among available wireless networks. So for example, from cellular data network to WLAN and WLAN to cellular, etc. You can have adaptive selection of available radio resources. For example, you can have cognitive MIMO, selection among different wavelengths, etc. And then you have increased interoperability, for example, law enforcement and public safety applications. So let's talk about dynamic spectrum access. So the radio spectrum, as you all know, is consisting of different frequencies. So and you have different spectrum bands for different services. So if it is a satellite communication, or it's a airline communication, or if it is a general mobile communication, etc. So depending on the services, you have different spectrum bands. So this is a picture of the United States frequency allocation. So this is the radio spectrum and that you have, okay, and you can see that the radio spectrum is quite crowded, okay. So dynamic spectrum access is very important because the spectrum is crowded, but also it is underutilized. So when I say crowded, that means that the different portions of the spectrum, let's say these colors actually stand for different applications. So if you zoom into this picture, okay, or you can look up in this picture on the internet. This is a very popularly available picture. So you will see that these colors stand for different applications, okay, or different services, and you can see that the spectrum is allocated to so many services, okay. So in that way it is crowded, but for a particular service, let's say this particular color, okay, let's say when you are allocating this portion of the spectrum to a particular service, then you can see that the spectrum is not fully utilized at all times, okay. So there is a statistical aspect here. So spectrum actually is underutilized, okay. There will be heavy usage at certain times, but most of the time there will be either sparse use or medium use, okay. So there are a lot of spectrum free spaces or spectrum holes. So these are called spectrum holes, okay. So less than 6% is fully occupied actually on the average. So you can use these spectrum holes basically to your advantage, okay. So these spectrum holes are also sometimes called white spaces, okay. So as this diagram shows, that you have these portions of the spectrum which are under use, and then you have these white spaces, okay. So dynamic spectrum access means using these white spaces for other types of communications, okay. So that's what is cognitive radio meant for. So if you have a cognitive radio, okay, so it has some cognition and it can sense the radio environment. So it will always sense where is a white space, okay, and then it will use that white space frequency for some communication, and then when there is no white space, it will jump to the next available white space, it will jump to the next available white space, and so on. And in this way, dynamically it will access all the white spaces within the spectrum. So that is what dynamic spectrum access is for. So dynamic spectrum access can be two types. So there it can be overlay or underlay, okay. So let's say these are your primary users who have purchased the spectrum, okay. So they have licensed the spectrum. So these primary users are the licensed users, okay. And you can use the unlicensed part of the spectrum, okay. So you can be overlay. So this is the opportunistic use of the fallow spectrum. Okay, so these are the overlay. So these are the using the actual spectrum holes or the white spaces. However, you can also use the licensed portion of the spectrum by a method called underlay. So this is a non-interfering usage. Okay, if you are not interfering with the primary users, so these will be very low power usages. Okay, so compared to the primary user spectrum, these are very low power interferences. Okay, so the primary user will see these as low power interferences, so you can still use in this manner, and that is called underlay. Okay, so you can use the spectrum dynamically through overlay and underlay. Okay, so here is a picture which shows you the different components of a cognitive radio system. So you have unlicensed band, and then you have licensed band 1 and licensed band 2. So there will be primary base stations operating in the licensed band, and the primary users are using the licensed band. Okay, they can also form peer-to-peer ad hoc network within the licensed band. Okay, then you can have cognitive radio users which would use the unlicensed band. Okay, there will be a cognitive radio base station, and it can either, the cognitive radio users can either use the unlicensed band, or they can opportunistically use the licensed band wherever there is a white space or spectrum hole. Okay, and then there is a spectrum broker. Okay, so that will basically allot the white spaces or the unlicensed spectrum spaces to different cognitive radio users. Okay, so this is how a cognitive radio network operates. So the major players for dynamic spectral access are, of course, the IEEE and other standards organization. In the US, you have FCC or Federal Communications Commission. You have Federal Office of Communication in the UK. You have the ComReg in Ireland, and there are also other regulators around the world. You might try to find out what are the regulators in China. Okay, I apologize for my ignorance. So I am not aware of the regulators in China. So you can find it out yourself. You can take it as a exercise for yourself. Then you have the US Department of Defense. There are several industry players as well, and also several law enforcement and public safety agencies as well. So talking about regulators, so the FCC addresses cognitive radios in several notices of public rulemaking. The US President Spectrum Policy Initiative is there. In Canada, Japan, South Korea, and EU, there are different regulators that show interest in more flexible allocation of spectrum. In the industry, you have this White Space Coalition and Wireless Innovative Alliance. So they are mainly responsible in delivery of broadband internet using the white spaces in TV spectrum. Okay, so the part of this coalition is big names like Microsoft, Google, Dell, HP, Intel, Philips, Samsung, Earthlink, etc. In South Korea, you have ETRI, who took part in the development of the IEEE 802.22 standard, which is related to cognitive radio. In Japan, you have this NICT, which was responsible for the development of software-defined cognitive wireless networks. Numerous EU supported partnerships between industry and academia also exist. And then, as I said, there are several applications of cognitive radio. So you can have them in wireless body area networks, you can have them in smart cities, you can have them in public safety networks, okay, and many other applications. Okay, so yeah, so as I said, smart grid, wireless cellular networks, public safety networks, wireless medical networks, and many more applications of cognitive radio exist. So this is one application of cognitive radio for healthcare. So if you have a remote hospital or remote medical research center, or a data center that stores health data, so you can have different cognitive radio sensors in your body, forming a wireless body area network, and then they can communicate using the different white spaces or different free spectrum holes, and they can communicate through a gateway and a cognitive radio base station to the internet, and then all this healthcare data that these cognitive radio sensors gather can be sent to the data center for storage, or directly to the hospital or medical research center for diagnosis or medical research. So if you are interested to know more, you can read this paper which is mentioned here. And I also encourage you to find out more applications of cognitive radio and read about them. So this is a topic which is not found in a textbook, so the more you can read, the better it is. If you are interested, you can read from the different research papers available. So with that, I will stop here today. So this is the end of this video lecture. I will see you in the next lecture. Thank you.